Hey, this is Avi Gutman with another Ask Me Anything event brought to you by quantreasoning.com. I invite you to join me live next time. We do this every Saturday at 11 a.m. Eastern, and you can attend for free by starting your free trial at quantreasoning.com. So I think there's a lot of work that can be done in this question. But I think it's important to do the work in the right order, if that makes sense. So, I think the very first thing we should do, given that they're talking about a median, is think about what would be the median of a set of 5 numbers. We've got a set of 5 numbers here. One of them is unknown, but in general, what would be the median of a set of 5 numbers? How would you find it? If we arrange the 5 numbers in ascending order, the median will be the middle number. That's right. Now we can arrange them in ascending order with one exception, right? We don't know exactly where x fits into the picture, but we can arrange 1, 3, 8, and 12 in ascending order, and then we can just note that there's also an x, and we don't know where the x belongs. So let's just put x in a cloud on top and kind of signal to ourselves that we don't know where x fits in this picture. What could the median be? There's not that many options. I mean, if x is all the way on the left, the median would be what?
3.
The median would be 3. If x is all the way on the right, the median would be
8.
8. And are there any other options for the median?
X could be median.
X could be the median if x is somewhere between 3 and 8. That's right. So those are all the options. So I think it's important to do that thinking, I guess, here. Like pause at that point and do the thinking that we just did. So now I'm ready to read on, and they're asking whether or not that median is greater than the average of the 5 numbers. So this is a yes-no data sufficiency question. And what do we know about the average of the 5 numbers? The average in general is defined as the ratio of the sum of the terms to the number of terms. That's like the definition of average in the dictionary. So if we add these terms together, I mean, I'm seeing a 20 there and another 4 there, so 24 plus x, and there are 5 terms. So the average is 24 plus x over 5. That's what the average is. We want to know whether or not the median is greater than that average. So I think that's where we want to start with this question, and hopefully we can do all of that work in about half a minute. Now we're ready to look at the statements. And it's important to always look at both just so that you can kind of decide which one you want to start with. You'd want to start with the easier one to evaluate. But as I look at these statements, I mean, the first statement is easy to comprehend. It's just saying x is to the right of 6 on the number line. But the second statement says that x is greater than the median. And remember, in our initial analysis, we said the median could be either 3 or x or 8. And now we're told that x is greater than the median, so what can you infer from that? What does it mean if x is greater than the median?
X is greater than 8.
That's right, it means that the median itself must be 8, and x is greater than 8. So we can rephrase statement 2 to 8 is the median, and x is greater than 8. That's a really important inference. I guess there's kind of 2 steps to that inference. Step 1 is, hey, if x is greater than the median, that means x is not the median. And if x is not the median, then the median must be either 3 or 8. But the only way that the median would be 3 is if x is less than or equal to 3. But we were told x is greater than the median, so the median isn't 3 and it isn't x, so what's the median? It's 8. And we were told that x is greater than the median, therefore x is greater than 8. So that's the whole chain of inferences that got us here for statement 2. And now when I compare this statement to statement 1, I can't help but notice that Statement 1 doesn't add any value in the context of statement 2. Like if we already know from statement 2 that x is greater than 8, then statement 1 isn't adding any value. If it's greater than 8, of course it's greater than 6. So given that we know statement 2, statement 1 adds no value, and as I explain in the second section of my book, that means we can eliminate answer choices A and C without even reading the question. Because think about what answer choice A says. It claims that statement 1 alone is sufficient, even though statement 2 alone is not sufficient. To which we would say here, hang on a second, if statement 1 alone is sufficient, statement 2 would be even more sufficient. Statement 2 gives us more information than what statement 1 had to offer. I mean, I'm imagining a situation where I'm at a job interview and they tell me that my pay will be more than $20 a year. And I'm like, okay, how much more than $20 a year? And then they come back the next day and they say, okay, actually it'll be more than $50 a year. Well, okay, so that's better, right? More than $50 a year is a bit better than more than $20 a year. But imagine it was the other way around. Imagine on day one they say, you're going to get paid more than $50 a year, and then I ask some follow-up questions about that, and they come back and say, okay, we'll give you a bit more information. It's actually going to be more than $20 a year. Well, that's not, you know what I mean? Like I already knew that it's going to be more than 50. You're not adding any value. So it doesn't make any sense that statement 1 would be sufficient on its own when statement 2 is not sufficient on its own. The other way around could be true. But not this. So A is gone, and C is also gone because think about what answer choice C says. Even though alone they're not sufficient, when you combine them, you get this miracle of sufficiency. But how could combining them wouldn't be useful if one of them doesn't add any value on top of the other? So we can eliminate A and C without even reading the question. And that, I think, is a great strategy for hard questions because we can improve our probability of guessing correctly. All right, so which statement do we want to start with now? 1 or 2? Which one do you think is going to be easier to evaluate?
Probably 2 by that logic.
I agree. I think statement 2 is going to be easier to evaluate. So let's start with that one. If we know that the median is 8, that's really what I like a lot about statement 2. With statement 2, we know for sure exactly what the median is. Whereas with statement 1, there may be some different possibilities for the median. So I feel like statement 2 is going to be easier to evaluate. We know exactly what the median is. And what can we say about the average for statement 2? I mean, if we know that x is greater than 8, then 24 plus x over 5 would be greater than 32 over 5. What I did there is I plugged an 8 into x. We know that x is more than 8, so the average would be more than this. Right? So we know that the average is more than whatever that, 6.4 or whatever. So we know exactly what the median is. And we know the average is more than 6.4. So who's bigger? I don't know. Right? Average could be 6.5, average could be a million. Which is bigger? I don't know. We can eliminate B and D. Because statement 2 is not sufficient on its own. Are we done? That was cool. We know that the median of a set won't be impacted by outliers. Does everybody know what an outlier is? It's when you have a member of a set that's way, way, way away from everybody else on the number line. You've got your set of numbers, let's say single-digit numbers, positive numbers, and then all of a sudden you have one member of the set that's a billion. That billion is an outlier. It's way far from everybody else. And one of the biggest conceptual differences between a median and an average is that a median kind of ignores outliers. Right? The outliers don't really impact the median because you get the median by arranging the numbers in ascending order, and whichever one is in the middle there, or if it's an even number of terms, then the average of those two middle numbers would be your median. So it's really not impacted by outliers. On the other hand, an average is very much impacted by outliers. It shouldn't be too difficult to find cases in which the average is greater than the median. Because our x, as you said, Vivek, the x is not bounded, it doesn't have an upper bound in either of the statements, right? Statement 1 says it's more than 6, statement 2 says it's more than the median, so there's really no upper limit. There's nothing preventing x from being a billion. And if x is a billion, then of course the average would be greater than the median, because that huge number, a billion, would impact the average but not the median. And so if we understand all of that, then in order to prove insufficiency, we don't need to worry about finding a case in which the average is greater than the median. We know that that's possible. Just make x a billion. All we need to do is show that the median could be greater than the average. Like, it's possible for the median to be greater than the average, because if it's possible for the median to be greater than the average, that gives us a yes. And from Vivek's insight, we already know we can get a no. We're done. Insufficient. I wonder if we can evaluate each statement on its own without pen and paper. Anyone want to try that challenge? Let's start with statement 1. I'll just note that m and n are both integers. They're greater than 6. We know the relative order of m and n, right? N is the bigger of the two. We want to know how big is that bit number that's the bigger of the two. And statement 1 tells us that their greatest common divisor is 6. Can you evaluate that without pen and paper? We know that there are two different positive integers, greater than 6, whose greatest common factor is 6. Can you tell me what the bigger of the two is? Yeah, and let me show you a visual just to help you see that a little bit better. We can tell from statement 1 that the prime box of m looks like that. The prime box of n looks like that, with a caveat that these ... and these ... they're completely distinct. So, in m, I could have 5 squared, 7 cubed, and in n, I could have 11 to the power of 5 and 13 to the power of 7. As long as that leads to n being greater than m, then anything goes. Anything goes. As long as those ... don't have anything in common, then the greatest common divisor of m and n is 6. And can we tell what the value of n is? No, there's an infinite number of possibilities. So that eliminates the answer choices that claim that statement 1 is sufficient on its own. Can we evaluate statement 2 without pen and paper? We want to think about two positive integers that are greater than 6, such that their least common multiple is 36. I think the easiest option to think about is when one of them is 36. And it would have to be the bigger of the two. So let's imagine that n is 36, and m then could be any factor of 36. So m could be 18 or 12 or 9. I think those are the possibilities for m. Nine, 12, or 18. Now, those all lead to the same answer. Those all lead to the answer that n is 36. So we just need to consider, is it possible that n is some other number other than 36? If n is 18, what would that mean for m, given that we want their least common multiple to be 36?
12.
Any other options?
Well, no, that's it.
The reason I asked if there are any other options is for the next phase of solving this question. I mean, from these two options, we can already eliminate b, but now that we know that these are all of the options, we just have to ask ourselves, do these two options still work with statement 1? Once you bring back statement 1 into the fold, do these options still work?
Yes.
This one definitely still works, right? The greatest common divisor of 12 and 18 is 6. What's the greatest common factor of 9 and 36?
9.
9. And what's the greatest common factor of 12 and 36?
12.
And what's the greatest common factor of 18 and 36?
18.
But statement 1 told us that the greatest common factor of m and n is 6. None of those works for statement 1, leaving us with only one possibility, meaning the correct answer is C. Now, some of you might think, hey, why is Avi testing cases? Avi hates to test cases. He never tests cases. There's an exception to every rule, and I'll say if there's a very small number of possible cases, it's absolutely appropriate to test cases. Sometimes you have no choice. Where I take issue with testing cases is when there's an infinite number of possible cases to test, and now I'm just kind of testing cases blindly and hoping to get lucky, hoping for the best. Here, though, when you look at statement 2, there were only 4 possible cases. It was 9 and 36, 12 and 36, 18 and 36, or 12 and 18. That's only 4 cases. Statement 1 on its own had an infinite number of possible cases, so I wasn't testing cases there. There we did it conceptually with the prime boxes. But with statement 2, there's only 4 cases. So write them out. That's absolutely what we should do. Hey, I'm just going to interrupt my own video for a moment here. If you're finding value in this video, please let me know in the comments below. And give this video a thumbs up. It really motivates me to keep uploading a new video every day. Alright, back to the video. The number 864 is obviously an important number for this question. And I'm wondering, if you all had to divide 864 by 3, how would you do that? And I hope you won't say long division. How would you find out 1/3 of 864?
900.
Good, exactly. You'd think of it as 900 minus 36, and then you divide each separately by 3 and solve from there. So when you look at the number 864, if your brain automatically translates that into 900 minus 36, then you have a chance to really speed up your work on this question. Because what's special about 900 and about 36? They're both perfect squares. And what do we know about the difference of squares? Exactly. And this is one of many reasons why I recommend not using long division. People who just use long division their whole life would never have a chance of noticing this. But people who use reasoning instead are much more likely to think of 864 as 900 minus 36, and then are much more likely to notice that that's 30 squared minus 6 squared, also known as 30 minus 6, 30 plus 6. So that's 24 and 36. Now it's not surprising that we were able to factor down the number to some number in the 20s multiplied by some number in the 30s. We already knew from the question stem that that's possible. The big question mark, though, is there another way to break down 864 into 2 factors such that one of them is in the 20s and the other is in the 30s. In fact, we should be able to say that, yes, there must be at least one more way, because otherwise we don't need statements. And that's not an option in data sufficiency. You always need at least one of the statements. So just from this question stem, and just from the fact that it's a data sufficiency question, we're guaranteed that there's at least one more way to get 864 as your product by using a factor in the 20s with a factor in the 30s. So let's see if we can find a more efficient way to look at this. What if we do the following? What if we ask ourselves, is 30 an option? Is 31 an option? Is 32 an option? Just go one by one, and there's only 10 numbers in the 30s. And we can eliminate a lot of them from consideration. I mean, 30 has a 5 in its prime box, so that's not an option. 31 itself is prime. 32 works, because 32 is 2 to the power of 5. And what would you have left there? 3 threes, which is 27. Okay, so that works. 33 has an 11 in the prime box, so that doesn't work. 34 has a 17 in the prime box. 35 has a 5 in the prime box. 36 we already found, it goes with 24. 37 is a prime. 38 has a 19 in it. 39 has a 13 in it. So none of those work, and so now I know what are the two cases that we need to consider. There's 32 times 27, and there's 36 times 24, and they're asking about the square. So it's either 2 or 2 or 6, and we don't know which it is. Is it 2? Or is it 6? I don't know. So I do need statements. But I think each of these statements on its own points us towards the 6. That's from each statement on its own, and therefore the answer is D. And I think the big takeaway here is, look, there's only 10 numbers in the 30s, and it's pretty quick to rule out the ones that you couldn't make up using the primes that are available to you, which again, there were 5 2s and 3 3s. And you can get that from here, right? That's 3 times 8, 3 is a prime, 8 is 2 cubed, and then 36 is 6 times 6, each of those is a 2 and a 3. So you can count them all up and see that you have a total of 5 of these and 3 of these. So I can't make 30 or 31 or 33 or 34, etc. So we're ruling them out very quickly thanks to the prime box. I think that's probably the piece that a lot of people miss on this question. I think it could be done in 2 minutes even without my awesome difference of squares insight. Let's do this together. So 864, I'm going to prime box it. So I'm going to start by noticing that 8 is a factor, and I see that because it's funny. Now I'm looking at it as 800 plus 64. So earlier I looked at it as 900 minus 36. Now I'm looking at it as 800 plus 64, each of which is a multiple of 8. There you have a 2 cubed. And by the way, how I got 108 is I thought of it as 800 plus 64. 800 divided by 8 is 100. 64 divided by 8 is 8, so it's 108. So that's 2 times 54, and that's 2 times 27, which is 3 cubed. So how long did it take me to find 2 to the 5 3 cubed? So then you do this, and you say that has a 5, that has a 31, that has an 11, that has a 17, that has a 5, that has a 37, that has a 19, that has a 13. So we're left with 32, which would take all of those, leaving us with a 3 cubed. And you have 36, which would be 2 squared, 3 squared, leaving us with 3 2s and a 3. So that's 24. If you found this video useful, go to quantreasoning.com for a lot more where that came from. You should also click that like button and let me know in the comments below what you'd like me to make future videos about. And of course, if you haven't yet subscribed, go ahead and do that and click that bell below so you get notified about future videos. See you next time.